Okay, hello everyone. This is the test number 2 practice sheet solutions. So you might hear a cat whining in the back. He's having a bad day. So just if you hear a meow, it's just a cat. So anyway, we'll get right into it. We'll solve problem 1. So the first thing it's asking is to find the derivative of the function x cubed plus 11x plus 100 divided by x squared minus 17. So to put that in math speak, we're going to put the d by dx here. So we're taking the derivative of this fraction, right? And then our clue of what type of derivative we're going to do, or what type of rule, sorry, that we're going to use, right, is the fraction, right? So we've got a function divided by a function. Here's the cat. We've got a function divided by a function, and the rule that says when you've got a function divided by a function, if you want to take the derivative of that, it should use the quotient rule, right? So doing that, what is that? So we've got the bottom times the derivative of the top. So I won't actually take the derivative yet. I'll just put this little notation here to say that I am going to take the derivative, but not just yet, right? So bottom times the derivative of the top minus, it's very important you put the minus. So the bottom divided by, or the bottom times the derivative of the top minus the top times the derivative of the bottom. And you got an x squared minus 17, right? And then you take all of that and you divide by the square of the denominator, right? So remember that little thing that we discussed in class, the low d high minus high d low of the square of what's below. So now we can actually go through and calculate the derivative. So the derivative of this bit right here, we'll do first. So the derivative of x cubed plus 11x plus 100. So we've got 3x squared plus 11, right? Then we got the minus sign. Then the x cubed plus 11x plus 100 stays. Then we multiply by the derivative there. So that's just 2x, right? So that's the derivative we just took right there. And then the bottom stays the same. There's really no sense in expanding it because it's just going to give you a big mess. So you could leave it like this if you wanted, but just for the sake of cleaning it up a little bit, we can expand the top and simplify it a bit. So when we expand the top, so we'll just do our distribution, right? So we'll just like multiply that in, multiply that, right? So just keep doing this distribution here, right? So you've got 3x to the 4 plus 11x squared minus 51, not 15, 51 x squared minus 187. So that's the distributing the first part. Then you've got this negative sign coming from right here, and that's going to dictate a lot of negative signs over here. So then when we distribute over here, we end up getting minus 2x to the 4 minus 22x squared minus 200x. Right, that's all divided by x squared minus 17 squared. Okay, so we've got that, and then we can bring together the like terms. So there's a x to the 4 and an x to the 4 here. There's an x squared term here, another one here, and another one here. And then there's only an x term left there and a constant term right there. So just bringing everything together, let's see, so 3x to the 4 minus 2x to the 4 is just 1x to the 4, so you got x to the 4. Combining the other ones, you end up getting minus 62x squared minus 200x minus 187 all divided by x squared minus 17 squared. And that is the derivative. Okay, next we've got problem 2. It says, using the graph of the piecewise function f below, find the value of f prime of 0 and f prime at 3. So remember what the derivative means, right? Remember, so you have to be slightly careful here. It's f prime of 0 and f prime at 3. So the derivative, f prime, tells you the slope of the tangent line at that given point, right? So here, what it's asking you, right there, what is the slope of the tangent line of the graph of f at the point where x equals 0? Okay, so if we look at the graph and we go to where x equals 0, and we draw a tangent line, we go, okay, well, we'll draw a tangent line there, and that's that point there, right? So the thing to really notice, right, is that, well, first, it's a horizontal line, so we know that the derivative is 0. But the thing that I really wanted you to notice was that at the point where x equals 0, so at this point here, right, it's a relative maximum. So we know from class that at relative maximums, the derivative is 0. So just from looking at that, it would have been good just to say, oh yeah, it's a relative maximum, so we know that the derivative is 0. But just to be sure, we can draw a tangent line right there and go, okay, yep, makes sense. It's got a 0 slope, so we're safe to say f prime of 0 equals 0. Now for the next one, f prime of 3, so if we go over to x equals 3 and we go down, right? So at that point, we want to figure out what the derivative is. So remember, the derivative at that point is the slope of the tangent line. So really what we're doing is we're just drawing a tangent line to that point. And if you notice is that if I draw a tangent line, it's actually just the line itself, right? If I drew it properly, you'd see that. But so if you draw a tangent line, see, it just matches right over. So really all we have to do is we just have to calculate the slope of that line, because the slope of that line that's given will be the derivative. So what we can do is we'll notice that we've been given some pretty nice points, right? So we can use the y2 minus y1 over x2 minus x1 formula, right? So so I've highlighted 2 points here, right? So let me just put it in a different color here. So there's a point here at 2, 2, right? So the line goes through the points 2, 2, and then there's another one here where it goes through 3, negative 1. Okay, so we know from the slope formula, which is on the formula sheet, by the way, so the derivative at 3 is going to be y2 minus y1 over x2 minus x1 in this particular case, right? So it doesn't matter what we pick the x1, y1, and x2, y2 to be, as long as we're consistent in the way that we're subtracting, it's okay. So just to make this clear, we're just going to pick x1 and y1 to be 2, 2, and we'll pick x2 and y2 to be 3, negative 1. Okay, so following this formula here, so we'll say, okay, well, f prime of 3 is equal to minus 1 minus 2 divided by 3 minus 2. So this is negative 3 over 1, which is negative 3. Okay, so the slope of the tangent line, or the derivative of f at the point where x equals 3 is equal to negative 3. And this kind of makes sense, right? So we've got the slope here says is negative 3, and if you take a look at this line, that really does look like a line with a slope -3. So it works out. So the first problem here, so we found that this f prime of 0 was equal to 0 because we're at a relative maximum. And then we calculated that this slope was -3. So f prime of 3 was equal to -3 by the slope formula. So for problem 3, it's asking to use the limit definition of the derivative to calculate the derivative of the function 2x squared plus 3x plus 4. So we know from the derivative rules that this thing is going to be 4x plus 3 just by looking at it. But on the test, I might ask you to do something like this. So we'll go through that. So what we want to use is we want to use this formula. Okay, so we're just going to go ahead and start calculating that. So we've got the limit as h goes to 0 of now f of x plus h. So that means everywhere where you see an x, you stick x plus h. Right? So you got x plus h squared plus 3x. Oops. Plus 3x plus h plus 4. Right? So that this bit here is f of x plus h. Right? So it's f of x with x plus h stuck into it. Okay, so we've got that. Then we subtract off just the regular function f of x. So we got 2x squared plus 3x plus 4, all divided by h. Okay, so now let's just kind of go through the math here. So this is equal to the limit as h goes to 0. So do not forget to put your limits down. So you've got 2 times x squared plus 2xh plus h squared plus 3x plus 3h plus 4. So that's just expanding this bit here. Right? And then we'll distribute the negative sign in. So we've got minus 2x squared minus 3x minus 4. And this is still all over h. Okay, so then just to make this really clear here, what we'll do is we'll distribute that 2 in. So we'll have 2x squared plus 4xh plus 2h squared plus 3x plus 3h plus 4 minus 2x squared minus 3x minus 4 all divided by h. Okay, so now we're in a good position just to start canceling out terms that cancel. Okay, so we've got that canceling with that. Let's see what else cancels. We've got the 3x canceling with the minus 3x. And we've got a positive 4 canceling out the negative 4. And that looks like that's pretty much everything that cancels for right now. So we'll rewrite this as 4xh plus 2h squared plus 3h all divided by h. Now though, I want you to notice now that you've got an h here, an h squared there, an h here, and an h here, right? So there's an h in every single term. So that means that we can, at the very least, factor out one of them, right? And that's actually what we want to do. Because we want to get rid of that h that's in the denominator. Right, so if I yank out an h on the top, so factor that out, you get 4x plus 2h plus 3, all divided by h. And then you got this canceling of the h's. Right, so now this thing looks really nice. So now this is the limit as h goes to 0 of 4x plus 2h plus 3, right? So then as h goes to 0, that thing goes to 0, and the only thing that you're left with is 4x plus 3, right? So if you look back up at the top, right, remember the original function that we started with, right, was 2x squared plus 3x plus 4. And like I said before, just by looking at that, knowing the power rules for derivatives, we would be able to say pretty easily, well, that should be 4x plus 3, right? And there you go. We calculated that to be 4x plus 3. So that's good. For problem 4, it's asking find all critical numbers for the function f, which is given by x divided by x squared plus 121. So remember, critical numbers for a function are where its derivative is equal to 0 or where its derivative does not exist. So first things first, we need to figure out what the derivative is. So let's see. So the derivative, we can use the quotient rule, right? So that's low d high. So low times the derivative of the high thing minus high times the derivative of the low thing, all divided by the square of the bottom, right? So let's figure out what these derivatives are. So we've got x squared plus 121 here. The derivative of x is just 1, so there's just a 1 there. Then we've got minus x times the derivative of x squared plus 121, which is just 2x, using the power rule, right? And then the bottom stays the same with the square. We can simplify the top a little bit, right? So this is actually x squared plus 121 minus 2x squared, all over x squared plus 121 all squared. And then that simplifies to minus x squared plus 121 all divided by x squared plus 121 all squared. Okay, so now we have to figure out where does this thing equal 0 and where does it not exist. Okay, so where does f prime equal 0 and where does it not exist? So from class, remember, if we take a look at the denominator first, if the derivative isn't going to exist, right, there's going to be some issue with the denominator. And in particular, it's when the denominator equals 0. But remember from class, what we talked about was that, so in this case, you got x squared plus 121, right? And remember that that can't be 0 because x squared is always bigger than or equal to 0, and 121 is always bigger than 0. So if you add two things, one of them which is always bigger than 0 together, and the other one is bigger than or equal to 0, there's no way for you to be 0, right? So the bottom is never 0, so this tells us that the derivative f prime exists everywhere. You don't have to go into too much detail with that. Just note that the bottom's never 0, so we're okay. Okay, so f prime exists everywhere, so we're good. Okay, so next, so where is f prime equal to 0 then? Right, because remember, critical numbers are the x values where the derivative is 0 or where it doesn't exist. So where does this thing equal 0? So f prime equals 0 when the derivative minus x squared plus 121 over x squared plus 121 squared is equal to 0. Now remember, again from class, when you've got a fraction and you set that equal to 0, we don't care about the denominator anymore. We only care about when the numerator is 0, right? So really what we're looking for is when minus x squared plus 121 is equal to 0. Okay, so just rearranging this, this is the same thing as saying, when is x squared equal to 121? So then if you just take the square root of both sides, you end up getting x is either plus or minus the square root of 121. And if you take the square root of 121, you'll notice that that's 11. So x is plus or minus 11. So x equals minus 11 is a critical number. And so is x equals 11. Okay, so next up we've got problem 5. This is consider the function f given by x cubed over 3 plus x squared over 2 minus 2x plus 30. Find all critical points of f and classify each as a corresponding to a relative maximum, relative minimum, or neither. So first thing, remember critical points are when the derivative is either 0 or doesn't exist. However, we can tell from just the function right now, it's a nice polynomial, so the derivative is always going to exist. So we're only going to really care about when the derivative is 0. But again, first things first, what we need to do is we have to figure out what the derivative actually is. So we have got f prime equals 3x squared over 3 plus 2x over 2 minus 2 plus 0. Right, so we just use the power rule on each of those things and the constant rule on the 30, which is where the 0 is coming from. Then, so then what's happening is we got a little bit of cancellations going on. So the 3 cancels with the 3, the 2 with the 2, and then we can simplify this to be x squared plus x minus 2, which very nicely factors to x plus 2 times x minus 1. Okay, so now we want to know where is the derivative equal to 0, right? Well, this equals 0 when x plus 2 times x minus 1 is equal to 0. And this happens, right, so this happens when either x is equal to minus 2 or x is equal to 1, right? So those are our critical numbers. So then what the next part is, remember from class, is we plot these on the number line. So we'll draw a little number line here. We'll go, okay, well, we've got -2 there, and we've got 1 there. Then we pick some test points. So the test points we'll pick, so say, pick -3 to the left of -2. Then we'll pick maybe 0 in between -2 and 1. And then we'll pick, say, I don't know, 2 to the right of 1, okay? Then remember what the next part is that we plug these numbers into the derivative and check the sign, right? So we'll check f prime of -3. So we'll plug that into the derivative. So that's -3 plus 2 times -3 minus 1. So that's going to give you 4, which is greater than 0. So this tells us that the function f, the original function f, is increasing on the interval x less than -2. Okay, so that's good. Plugging in 0 into the derivative. Okay, so that's 0 plus 2 times 0 minus 1, which is just -2. That's less than 0, so we've got the derivative is less than 0 in that interval. So that tells us that the original function f is decreasing on the interval -2 to 1. And then finally, we'll plug in the last test number 2. Okay, so that's 2 plus 2 times 2 minus 1, which is just 4, which is greater than 0, right? It's positive. So therefore, f is increasing. The original function f is increasing on the interval x greater than 1. Okay, so now with this information, we can make that little chart that we like, right? So we've got the direction of graph on the top. Then we've got this sign of f prime here. And then we draw this little interval thing, right? So we've got the -2 and the 1. And we know that, so to the left of -2, we were told, or we figured out that it was decreasing, right? The derivative was, oh, sorry, increasing. The derivative is increasing to the left of -2. So the derivative was positive, and therefore the function is increasing there. We also found that in the interval between -2 and 1, that the function was decreasing, and therefore the sign of the derivative, well, we found also that the sign of the derivative was negative. And then for the last one, we found that the sign was positive, which means that the function is increasing. Right, so we've got this little thing here. And then what's really nice about this setup is that you can kind of do these little, just follow the graph, follow the arrows, see what happens. So you can tell that when you do this, that -2 must correspond to a relative max. right? Because you see the little, the hump there. And then this one corresponds to a relative min, right? So if you're increasing and then decreasing, you're a relative max. And if you're decreasing and then increasing, you're a relative min. So what you would say is x equals -2 corresponds to a relative max, and x equals 1 corresponds to a relative min. Oops, spelled that wrong. Relative min. Okay, so for problem 6, what we're looking for is the derivative of the function given by 3x plus the square root of x all times x cubed minus 14x. So the idea for this one was to try to get you to be comfortable with the product rule. You're more than welcome to expand this out if you want and just use the power rule, but I'm going to do it with the product rule just so we can see how to do this. Okay, so for the first thing, so the derivative, we're going to use the product rule. So what is that? So that's the first, actually even before this, before we even start this, let's rewrite the function to make this a little bit easier, right? So notice that we've got a square root right there, right? So to make this a little bit easier on ourselves, we're going to replace that square root with a power of 1/2 because they're the same thing, but it makes doing the derivatives a lot easier. Okay, so that's the way that our function is going to look. We just replace the square root with the 1/2. Okay, so now we can do the derivative. So we got f prime, so it's first times the derivative of the second plus second times the derivative of the first. So if you're uncomfortable with this, remember that this is all on the formula sheet, so it's not that big of a deal, but hopefully you're comfortable with these rules so far. Okay, so that was the product rule. So now what we'll go through and we'll actually calculate this derivative here. So we've got 3x plus x to the 1/2. Then the derivative of the stuff in the brackets there, that's pretty easy, right? That's 3x squared minus 14. Then you've got plus x cubed minus 14x, that just stays. And then the derivative of the inside of that bit is 3 plus, then the 1/2 comes down, and then you got x to the minus 1/2, because 1/2 minus a half minus 1 is minus a half. Okay, so this looks pretty good so far. So the only thing, so really, I would be okay with you leaving it like this. This is correct. I mean, you can expand it if you want. You're more than welcome to. The only thing that I'm going to do is I'm going to just rewrite this as 3x plus the square root of x. So just get rid of the 1/2 powers, just to get comfortable with that. All right, so wherever you see a 1/2, stick a square root, right? So you've got, this stays the same, plus x cubed minus 14x times 3 plus, now for this bit, remember the 1/2 means square root, but also the negative in the exponent means it goes in the denominator, right? So this is 1/2 root x. Okay, so that's the derivative. You don't have to expand it if you don't want to. I would be fine with you leaving it like this. Okay, problem 7, the big scary infinite limit. Calculate the limit as x goes to plus infinity of 2x cubed minus 14x plus 2 divided by minus 4x cubed plus 11. All right, so actually this really isn't bad at all. You're able to use that trick that I mentioned before, and there's that PDF that I put on the website as well. The thing, whenever you're dealing with rational functions and infinite limits, you can just take a look at the numerator and the denominator and look at the highest powers of x. And the thing to notice here is that the numerator, the highest power of x is x cubed, and in the denominator, the highest power of x is also x cubed, right? So when you have that, all the infinite limit is the ratio of the coefficients in front of them, right? So it's just the ratio of the coefficients in front of these guys. So in particular, it's 2 divided by minus 4. Okay, so just to write it out, you will have the limit as x goes to plus infinity of 2x cubed minus 14x plus 2 divided by minus 4x cubed plus 11 is equal to 2 over minus 4, which is the same thing as negative 1/2. And that's it. This is a pretty easy question. So the thing with this, the only thing that I would ask you to say on a test, if this happened to have been a long answer question, is that you can either go through the whole thing where you divide everything by the biggest power of x from the denominator and do all that stuff. That's fine. But I'm also okay with you just saying, oh, notice that the numerator and the denominator have the same highest power of x. Therefore, the limit is the ratio of the two highest, the ratio of the two coefficients in front of the highest powers. So that's fine as well. So that one's that one. For problem 8, this is it's actually a very short problem. So it's just suppose you're given a differentiable function g that has a critical number at x equals 3. If you were told that g has an interval of decrease to the left of 3, so x less than 3, and an interval of increase to the right of 3, but less than 5, classify the critical number 3 as corresponding to a relative maximum, relative minimum, or neither. Now, the first thing I'm going to mention, and I've had a lot of students ask me this, is what's going on with the 5 there. And it's really nothing. It's just, it wasn't even really supposed to be a trick. It was just the way that I had written the problem. 5 really has nothing to do with this problem, right? If you read into the question, or sorry, actually don't read that far into the question. What this is saying is that you've got an interval of decrease to the left of 3 and an interval of increase to the right. Okay, so that's really what I was trying to say here. So the main critical point that we're interested in, the critical number is x equals 3, right? So when we draw this on the number line, right, so here's 3, we know that the function is decreasing to the left, right? And I'll put 5 in here just to make it so that it fully answers the question here. To the left of 3, we're decreasing, but then in the interval 3 to 5, we're increasing, right? So if you just kind of follow that along, it's easy to see that 3 must correspond to a relative minimum, okay? So that was the idea for this. So you would just say, so x equals 3 corresponds to a relative minimum. And that's it. Problem 9 asks to consider this piecewise function where you're equal to x squared plus 10 when x is less than 2, and you're equal to x minus 3 when x is bigger than or equal to 2. So all I'm asking you to do here is calculate the limit as x approaches 2 from the left, the limit as x approaches 2 from the right, and then conclude using those two things whether or not h is continuous at the point x equals 2. Okay, so this is going back quite a few lectures, so hopefully this is a little bit of a refresher here. So remember that this little bit here, x approaches 2 with the negative sign, right? That means we're approaching 2 from the left-hand side, right? And if we're to the left of 2, that means that we must be this function, right? Because we're equal to x squared plus 2 when x is less than 2, right? So when we're approaching h, when we're approaching 2 from the left of h, that's the function that we have to stick with. And similarly, when we're approaching 2 with the plus sign, that means approaching 2 from the right, which means that we're approaching 2 coming from the right-hand side. And then so the function corresponding to the right of 2 is x minus 3. So what we'll do is we'll just calculate these limits. So this is the limit as x approaches 2 from the left of h. So this is equal to the limit as x approaches 2 from the left. And remember, the left-hand function here is the x squared plus 10. Okay, and then so since this is a nice polynomial, the limit, you can just pretty much, you can throw in the number and it's fine. So you get 2 squared plus 10, so this is equal to 14. Then the limit from the right-hand limit, x approaches 2 from the right of h, is equal to the limit as x approaches 2 from the right of x minus 3, because that's the right-hand function now, right? So then since this is a nice polynomial, it's a continuous function, so you can plug it in. So this is 2 minus 3, which is -1. Okay, so we've got that the limit from the left as we approach 2 is 14, and the limit from the right as we approach 2 is -1. So now the big question is h continuous at x equals 2? And the big answer is no, right? So no, h is not continuous. Is not continuous at x equals 2. And the reason why is because it's kind of, you can see it from the limits, right? Because if the function's continuous, it means it doesn't have any holes or any gaps. So if you're approaching 2 from the left and you're 14, and then you approach 2 from the right and you're -1, that must mean there's a big gap between, so there's obviously a big gap between 14 and -1, right? So to say this mathematically, for a function to be continuous, we need, so for it to be continuous, we would need that the limit as x approaches 2 from the left of h has to be equal to the limit as x approaches 2 from the right of h, right? And we don't have that. Right, we don't have this. Okay, so that's why the function is not continuous. There's a big old gap there. Okay, we're getting near the end here. Problem 10. Find the second derivative of the function f given by 3 minus x all times 1 plus x to the minus 3 over 2. So the idea for this one was to use the product rule a bunch of times, but I've had so many students ask me about why can't we just expand and then take the derivatives, and you can. So what we're going to do is I'll just try to satisfy that that urge to expand, and we'll do that here. Okay, so we can rewrite f by expanding, right? So we'll multiply the 3 in, multiply the 3 there, multiply the negative x and then negative x there. So when we do this expansion, we get 3 plus 3x to the negative 3 over 2 minus x, and then you've got this minus x here. So you have to be a little bit careful. The minus x times x to the negative 3 over 2. So you have to be careful with your exponent laws. So when you multiply two things like that, you can add their powers together, right? So remember, there's a little imaginary power of 1 on top of that x. So when you multiply x and x to the minus 3 over 2, you can add their exponents, right? So you got negative 3 over 2 plus 1, which is negative 1/2. So we can rewrite this as x to the negative 1/2. Okay, so that's f rewritten. We haven't taken a single derivative here, right? And remember, you have to remember here, we're looking for the second derivative. Okay, so that's the derivative of the derivative. So first thing, to get the second derivative, we need the first derivative. So taking the first derivative, so that's d by dx of 3 plus 3x to the minus 3 over 2 minus x to the minus 1/2. Okay, so then we just take the derivative of each of those things. We end up getting 0 plus, so now we can use the power rule. So this is 3 times, so the negative 3 over 2 comes down, and we subtract 1 from the top, which is minus 5 over 2. Then you get a minus 1 there because the derivative of x is just 1. So derivative of minus x is minus 1. So that's why there's a minus 1. And then we've got minus, and then use the power rule. 1/2 comes down, x to the minus 3 over 2, because minus 1/2 minus 1 is minus 3 over 2. Okay, so we'll simplify this just a little bit. Negative 3 over 2 times 3, so this is negative 9 over 2 x to the minus 5 over 2. And then we've got a minus 1 floating around still, and then we've got negative 1/2 with a minus sign in front of it, x to the minus 3 over 2. So those two negative signs here, so the negative sign here and here, they combine to give you a nice little positive sign. So, so this becomes plus 1/2 x to the minus 3 over 2. You have to be very careful with this sign stuff because that's what's gonna screw a lot of people up on the exam and on the test. Okay, so now remember we want the second derivative, and the second derivative is the derivative of the derivative. So f double prime is the derivative of the derivative. All right, so we're taking the derivative of the thing we just found. Okay, so let's do that. So it's the same thing. So we take the derivative of each individual piece. So the minus n over 2 stays. We can bring down the minus 5 over 2, x to the minus, now minus 5 over 2 minus 1 is minus 7 over 2. The 1 becomes a 0 because the derivative of a constant is always 0. And then here, you've got the 1/2, and then using the power rule, that comes down, and then this becomes minus 5 over 2 because we have to subtract 1. Okay, so then just to simplify a little bit, you have 45 over 4 x to the minus 7 over 2 minus 3 over 4 x to the minus 5 over 2. Okay, and that's the second derivative. All right, you stuck with it. Problem 11, last one. Okay, so find the slope of the tangent line to the curve xy minus y cubed equals 2 at the point 2, 1. Okay, so there's a tiny little mistake in this problem. It's actually not going to affect your answer whatsoever, but the point that I gave you actually does not lie on this curve. So what I'm going to do, just for the sake of the correcting this, I'm going to get rid of this 2, and I'm going to replace it with a 1. Okay, so it doesn't change anything what we're going to do. It's just in case anybody was trying to figure out if they tried to plot this thing and it wasn't making sense. That's why. Okay, so I'm sorry for the confusion. Nothing's changing about how to do the problem. It's just that 2 should have been a 1. Okay, so using that, let's get started. So very first thing we notice is that it's one of those crazy kind of things where you got a bunch of y's floating around, and that's how you know it's going to be an implicit differentiation problem. So when we're doing this, we have to assume that y is a function of x, right? So y is a function of x. Okay, you don't have to write that down on the test. I know you know that this is what's going on. So, so the slope of the tangent line means derivative, right? So what we want is we want to find the dy by dx. So what we'll do is we'll take the derivative of both sides because that's really the only thing we can do at this moment, right? So the derivative of the left-hand side equals the derivative of the right-hand side. And remember, we've changed that 2 to a 1. Okay. So first thing we know is that the derivative of a constant is 0. So the right-hand side is 0. So that's good. So that's why it didn't matter if it was a 2 or a 1. It's just, it was going to be 0 anyway. And then just to simplify this just a little tiny bit, remember that we can use the sum rule here and say this is the same thing as the derivative of xy minus the derivative of y cubed, and this is equal to 0 from what we just talked about above, right? So on this little piece here, we can use the product rule, right? So in fact, I should have said use. So use the product rule, and then on this piece, we can use the general power rule. Okay, so let's go through that. So for the first one, remember what the product rule is, right? So for the first, we got first times the derivative of the second, right? Because remember, the derivative of y is just dy by dx. So first times the derivative of the second plus second times the derivative of the first, right? So the derivative of x. So that's that first bit, right? And then for the second bit, we've got minus, and then the derivative of y cubed, we have to use the general power rule, right? So the 3 comes down, you got the y squared, and then you have to multiply by the derivative of y, right? And then this is equal to 0. Right, that's just the general power rule. Okay, so now what we want to do, well, actually we can simplify this a little bit more. Remember here that the derivative of just x is 1. So we can rewrite this as x times dy by dx plus y times 1, or just leave it as y, so just y, minus 3y squared times dy by dx. And this is equal to 0. So remember from class, what we want to do is we want to keep everything with the dy by dx on the left-hand side and move everything else that does not have it on the right-hand side. Okay, so we've got x times dy by dx, and then we've got a minus 3y squared times dy by dx, and then we're going to bring the y. So we're going to bring the y over here, and that's why there's a negative y. Okay, so now the next step is we'll factor out a dy by dx. All right, so this is x 3y squared equals negative y. Okay, and then we just divide by x minus 3y squared. Right, so we just throw it in the denominator of the other one, and we want to solve for dy by dx, right? So this is minus y all divided by x minus 3y squared. Okay, so that's the derivative. We've solved for the derivative, but remember what the question's asking. The question's saying find the slope of the tangent line to the curve at the point 2, 1. So we found the derivative, which gives us the slope of the tangent line, so we just have to plug in the point 2, 1 to get it. Right, so we've got dy by dx. We put this little notation here, meaning that we're going to evaluate the derivative at the point 2, 1. So wherever you see a y, put a 1, and wherever you see an x, put a 2. Right, so this is minus 1 divided by 2 minus 3 times 1 squared. Okay, so this is minus 1 over 2 minus 3, which is minus 1 over minus 1, which is 1. Okay, so the slope of the tangent line is 1. Okay, and that does it. That's the practice sheet.